Okay, welcome to 2.7, multiplying, dividing rational expressions. The thing I want to emphasize here is that basically what we're doing with rational expressions is basically like algebraic fractions, and what we're doing is multiplying and dividing them. In the last lesson, or 2 lessons ago, we actually were simplifying them, and so it meant we were trying to find the lowest common denominator. Trying to put them in lowest terms. And so for multiplying and dividing fractions is very similar. And so we'll need lowest terms. We're going to need to cancel stuff out. And so what I want to do is show you, basically start with like 2 just number fractions. And the same logic we're going to apply with numbers, we're going to apply with algebra. And so I want you to try to factor these. And you can pause the video and try this on your own. And remember that factoring is not something for algebra. It is something that we do with numbers. And so if you want to pause it, and you can try this question. Okay, so the way we factor something like 25 is we factor it as 5 times 5. 78 we think of as 13 times 6, but also 6 can actually go down as well. And so we factor 78 as 13 times 3 times 2. Easiest way to do 78 is divided by 2, and then you get 13 times whatever. You get 39, then you can divide 39 by 3. And so every number you divide, stick around as one of the factors. You write 13 as 13 times 1 or just 13. It would actually be good to write it as 13 times 1. That way when you understand, when you cancel it out, you're left with the 1. Oftentimes students will cancel things out and not be sure what they're left with. I've seen students write 0. I've also seen students flip it when everything cancels out. And then 35 factors to 7 times 5. And the way it's written right now, you can actually just cross out things. Remember, the order doesn't matter when we're multiplying. So this 5 is really being divided by that 5. That 5 can be over there. To multiply fractions, we're just multiply the tops and multiply the bottoms, so that things can cancel out. 13s can go away, and we're left with, on the top is 5 and 42. We never ended up having to factor out the 6, or factor the 6 as 3 times 2, because in the end we multiplied 6 times 7 again. But it's a good exercise to go through to make sure we've got all of the factors canceled out. And then, I don't know if you knew this, but if you did fractions this way, this is actually guaranteed to be in lowest terms. It's easy to see in that sense. The 5 and 42 don't go into each other, but if you've canceled out all the factors, it's guaranteed to be in lowest terms. That's exactly what we're going to do with algebra. We've got 2 fractions multiplied together, and so we're going to try to factor them as much as we can. And so what we're actually just going to see is one strategy to do is to actually push the tops together, like x times 3 times y. And this is all things multiplied together. We rewrite the 6 as 3 times 2, so we factor out the 6 just like we did in the warm-up. 3 times 2 times 2 times x. And writing it like this, we can actually cancel out the 3's, we can cancel out the x's, and we're left with y over 4. You don't have to cross out the 6 like that, factor the 6 like that. In fact, we're not going to in the next one. But it is a really good strategy that I just wanted to model there. This is not quite equivalent. The top does have a restriction on x. X cannot equal 0. So for these 2 things to be equal, like we've said equal here, we do have to have a restriction on the denominator as well. X cannot equal 0. If x equaled 0, the denominator here would be 2 times 0, which equals 0. The next one, we've got a lot of factoring to do. I would actually encourage you to factor it even before you start thinking about canceling things out, much like we did with the numbers. Okay, so we've got on the top left here, and you can factor these. You can always pause the video and try it on your own, and then just play the video again. We put all the the lines here. We're going to do the top left. Factor out 3a. We're left with b plus 2. Remember that if you ever have trouble with that, you can always like distribute it back in and make sure it works. Always like emphasize checking. Factor out 5. We're left with a minus 3. 10. We're left with a minus 3. And then ab is just ab. It's factored. Another strategy I like to model is just pushing things together. You don't have to do this. Like, you can actually cancel things on the top and the bottom. We will do that, but I just wanted to show you this way as well. So you can see that things that can cancel, a minus 3s can go, the a's can go, the 10 and the 5 go. Notice we didn't factor 10 as 5 times 2. We recognize that 10 is 5 times 2, so we still have a little 2 left over. I think that's basically everything. On the top we have 6, so the 3 and the 2 become 6. And we've got b plus 2. On the bottom we have b. And then we go through the restrictions. We go through restrictions. On this line is the best because this is the fully factored line. And we remember we only look at the denominators for the restrictions. Numerators can equal 0. It's just the denominator can't equal 0. So here we see that b cannot equal 0. If b equals 0 here, it didn't really matter what a is. B times 0 times anything would give you 0, and you can't have that. A can't equal 0, so again, same thing here. And a can't equal 3, because if this was 3 minus 3, it would be 0. 5 times 0 is 0. Okay. Next one, division. So remember that the way we divide fractions is we flip and multiply. So we multiply and we multiply by the reciprocal of the second one. Remember, it's the reciprocal, not the negative reciprocal. So we just flip it. Because it's relatively easy to do, what I'm actually going to do at the same time is, just because I have the line, is to factor the 15 as 5 and 3 and the 8 as 4 and 2. Again, you don't have to do that, but it is a good strategy to model. The 2's cancel out. The 3's cancel out. What you could do is factor the negative 3 as negative 1 and 3. You don't have to. You just realize that like negative 3 is negative 1 times 3. And so when you cancel the 3's, you're left with negative 1. When we cancel out the x squared and the x cubed, we're left with x. You might want to factor x times x times x. X is x times x. And then x cubed is x times x times x. If you have 3 x's here and 2 x's here, you can see you just cancel them out one at a time. On the top we've got 5, and on the bottom we've got negative 4x. So just write the negative on the left or in the top, because if you leave the negative in the bottom, it's not generally good form, even though, as I say that, the negative is in the bottom here. Then we notice the restriction at this point here. It's important that we don't vigorously cross these out, because we actually need to read these afterwards. But like we can see, the restriction here is x cannot equal 0, and that's in the denominator as well. Notice that wasn't in the denominator originally, and we're going to talk about that in the next one. But x cannot equal 0. The second one, we've got a bunch of factoring to do. It's all common factoring. So we're going to factor the first one. Just flip and multiply before we factor the second one. You just don't want to do too much at once. The top left just factors as 6 times a minus 1. You always need to like check it out. You can see 6a minus 6. Top right is a times a plus 2. Bottom right is 3 times a minus 1. See the 3's cancel with the 6, and you're left with 2. The a canceled with the a squared, left with a. And the a minus 1's just cancel, and you're left with nothing. Or you're left with 1, and so if there's nothing else, you do have a 1. And on the top we have 2 times a plus 2, and on the bottom we have a. And so this is where I'm saying, like, don't vigorously cross this out. You do need to check to see the restrictions, and this is the line you want to go to. Here you can see a cannot equal 0, and here you can see that a cannot equal 1. There's also, like, back to here, like, notice that, remember that this x was a restriction. Well, likely this here actually was in the denominator originally. So since that was in the denominator originally, the root of that is -2. It was actually here. Numerators can have zeros. They can be 0. It's not the numerator's fault. But because that numerator was in the denominator originally, it's part of the restrictions as well. A cannot equal -2 up here, but remember that each one of these lines are equal as well. And the last one we're going to go through is divide. What we're going to actually do here is we're going to do the restriction, or we're going to factor it first so we can talk about that restriction. Just make sure we don't miss it. Before you kind of go to that next line, you probably want to pause it and try to factor each one of those things on your own. The top is a complex trinomial, and it's generally trickier to factor. But because it's 1 and 1, you can just use the guess and check method, and just highlighting that check, make sure it's correct. Decomposition, often we go through the steps of decomposition and we make a mistake anyway. And so 5, 2, and 1 and 1 are probably the numbers. I would factor these ones first, these three first. This is a difference of squares, so make sure you kind of recognize that. It's really important to recognize that because it makes it a lot easier to factor. It is a trinomial, it's just that the middle term is 0, and so the brackets have to be almost identical, except for one's a positive, one's a negative, so that the middle term will cancel out. So that's why it takes that difference of square shape. If you factor these, sometimes these can give you hints for what this might be if the complex trinomial is especially challenging. But as I said, this one, it's not that bad. So top left factors to 5x and 2x obviously is 10x squared. -1 and 1 is -1. It's the only way to get that. But just whether or not the negative is in the right spot. So we check it. We get 5x minus 2x is 3x. It's correct. There's a difference of squares. These are common factors. Before we flip and multiply, we actually take care of this restriction here. That restriction there, I don't want to kind of gloss over that. I want to take a little bit more time on that. What we actually do is we solve the little equation 3x plus 1 equals 0. This is very similar to what we do when we're solving quadratics, solving for the zeros in a quadratic. And so we put the 1 on the other side and divide by 3, just like solving a linear equation. If you do that once, you generally don't have to do it again. Like we're going to see maybe on this one, we're going to have to do it again. But really, you're just putting the 1 on the other side and dividing by 3. That's why it's a -1/3. So we just flip and multiply on the next line. 2x plus 1s can cancel out. 3x plus 1s can cancel out. And we're left with 4 times 5x minus 1 and 3x times 3x minus 1. Then just going through the restrictions, this one similarly is x cannot equal -1/2. It got canceled out. But just remember that it's still a restriction. It just means it's not an asymptote, it's a whole. This one's x cannot equal 1/3. That one didn't get canceled out. It's what you call a vertical asymptote. This one didn't get canceled out. It's x cannot equal 0. It's a vertical asymptote. And actually, this one here that got canceled out at the top, it was kind of insurance a little bit. We would have still got it if we had forgot about the one that flipped to the top. That doesn't always happen, but you can see that we've got 1, 2, 3, 4 restrictions for the 4 places that the x is in the factored form. It's very important that you factor it before you cancel, just to highlight that. A lot of people might want to cancel out these 1s or cancel the 6 and the 12, and you can't do any of that until you factor it. We just summarize the restrictions, just putting them all together because we kind of did them all over the place. So plus or minus 1/3, -1/2, and 0. Okay, and that's all for today's lesson.